Great. Well, thank you everyone for joining our seminar today. For your information, this seminar is being recorded and will be made available on the RemPlex webpage. And as a reminder, we request that you please keep yourself muted during today's presentation and Q&A. And my name is Alicia Gorton with Pacific Northwest National Laboratory, or PNNL, and I'll be moderating today's seminar on behalf of the Center for the Remediation of Complex Sites, or RemPlex. And RemPlex is a PNNL platform that couples unique core competencies and expertise with state-of-the-art facilities and physical assets to develop, mature, and deploy advanced technologies to solve complex issues of contaminated subsurface environments. And so today, we're joined by Chris Johnson and Patrick Royer of PNNL, who will describe how web applications minimize the complexity associated with large data sets and analytics, while maximizing productivity, promoting technical communication, and providing the technical basis for environmental decision-making. Chris Johnson is a chemical engineer who has performed a wide variety of R&D at PNNL since 1992 in the field of environmental restoration and remediation technology. Mr. Johnson has a long history of software development for environmental applications, including the RT3D code, which is a multi-species reactive transport simulation software, the soil vapor extraction end state tool, or SVET, and the plume analysis tool, or Plato, which is a module of the Socrates single page web application. And Patrick Royer from PNNL has extensive experience in the areas of cloud-based GIS applications, GIS applications for native and web environments, big data analytics. Additionally, his day-to-day skill sets include directing cloud development, database and data systems design, and big data management and numerical modeling. He has embraced cloud-based advancements and web application solutions, and has developed and maintained a GIS cloud model that serves as back-end to a broad user base of collaborators and product owners. And so after the presentation today, I'll facilitate a Q&A with Chris and Patrick, so I encourage you to type any questions you have into the chat box during the presentation. So with that, I will turn it over to Chris Johnson to kick us off. Chris?
Thank you, Alicia. So as we said, we're going to talk about web-based tools for environmental decision-making. And so that's for the overview. The challenge here is we need tools for environmental data access and analysis to meet needs for on the projects for consistency, quality, communications, and decision-making. So web-based software provides a good platform for rapid analysis and data access capabilities for disparate data from multiple sources. And the impact is the web-based tools are effective at providing consistent analyses to support quality requirements and remedy decisions on complex sites. So today, we'll go through what's the nature of environmental data, talk a little bit about data itself, talk about approaches to software tools for analysis, look at the web-based applications for using cloud computing infrastructure, and then finish up with some analysis to support decision-making. And when we look at some data visualization as well as some data analytics, and then talk about conclusions, benefits, and a broader perspective. So starting out looking at data sources, environmental data inherently comes in a lot of different forms and formats, and data access can vary among organizations. So this is common when you have multiple agencies or organizations or projects participating, and you can run into issues with things like overlapping authoritative data sources. It's supposedly authoritative, but they are overlapping between different agencies. So environmental data runs a pretty wide gamut of types. There's everything from electronic tabulated data, such as you might have for analytical chemistry data, for groundwater samples. Could be information about wells and waste sites. You have information from reports, which may be tabular, or could be figures, could be other kinds of data from reports. There are well logs or geophysical data, such as what we see over here, like a gamma log, for example. You might have sensor data, whether that's a downhole sensor or you have sensors monitoring flow rates and pressures and so on for a remedy. You can have spatial data. It could be point or polygon data looking at different features, GIS spatial type data. And you might go beyond that into 3D and look at 3D models of the subsurface or plumes. So 3D kind of data. And then finally here, you might have some satellite or remote sensing data that you'd apply to your site, everything from images to full data sets. So these different kinds of data can come in different forms. Tabular data is really a structured data where you have data fields in records, and you can store that in relational databases. You might have some of this be semi-structured data, which is not tabular, but it has a structure to it, and you can apply tags, such as in the center example here, where there's a property and a value. So JSON would be one format for that. Or you might have unstructured data, which are things like the documents, audio, sensor data might be unstructured data, and so on. And the nature of the data really comes into play in terms of how you store the data, how you access it, and what you can do in terms of manipulation of that data to use it in your analyses and lead to decision making. So as we're thinking about data, quality assurance is really a key concept, not only for the data, but for the calculations that go with it. And so data provenance, knowing where did this data come from, who generated it, what was done in terms of manipulation, that's really key information for users, consumers of that data. When you have an analysis, you're going to make some decisions, how do they have the trust, and is there credibility with that data? Can you reproduce the calculations based on that data? So those are really important pieces of information of where did that data come from. And a lot of times folks will use NQA1 as a quality standard. This is generated by ASME, and it provides a structured program of procedures to evaluate, review, and document both data and calculations. So again, this gets back to the trust and credibility. Where did this data come from? Was it reviewed? Have you documented that? Show me what you've done. So that NQA1 is a good standard for that. And really the key concepts are, can I trace the results back to the original data and be able to recreate what was done? Was this reviewed? Is somebody competent, subject matter experts review this and concur that it was done correctly and weren't mistakes? And in terms of software, were there requirements identified and then tested and then documented? Well, a few traditional approaches to software. If you've been around long enough, you typically used compiled executables on your desktop machine, and they'll do some calculations for you, present results, or you might use an Excel-based tool, such as the one displayed here. This is a screenshot of the suite software where you put calculations into the spreadsheet. And that's convenient because spreadsheets are pretty ubiquitous and people are familiar with those, easy to open a file and run that. But there's some issues with these sort of approaches, including potential installation issues on desktops versus mobile. Can you put it on your phone or not? If you have a spreadsheet tool, users have to have that Excel software to run that. You might run into version issues with the software or even the operating system that cause problems. Typically, these kind of approaches are less flexible in terms of data access and geospatial functionality. You can do some maps in Excel, but it's not really designed for that. And these sort of approaches are really geared towards indirect sharing of results. So with that, I'm going to turn it over to Patrick, and he's going to talk some more about other alternatives.
Yep. Thanks so much, Chris. Thanks, Alicia, for having us give this presentation. It's really a delight to talk about this and web-based apps. I've been involved, I guess, with these building and designing geospatial applications for over 10 years or so, and I've really seen this grow quite a bit. The focus today is more so on custom applications we've built using the cloud. I think it's important to note, however, that there are many commercial off-the-shelf platforms. There are indeed many different products, and sometimes it seems like there are so many, it's hard to choose which one to use. So I wanted to mention a couple of the more, I think, popular or well-known ones. I also want to say importantly that we use these, or I use these sometimes with a sponsor or collaborators when it's right to use it. And what I find most often is that we use an off-the-shelf product till we hit a certain point, and then we find we need to go custom based on the requirements. So a few of these, ArcGIS Online has some web mapping applications that are pretty easy to start using. It's meant for the non-expert user to be able to create some maps and share this information. It's pretty tightly bound, I think, to the ISRI ecosystem, which is this larger platform of using ArcGIS for server and some of their other tools. So we use ISRI quite a bit, and when it's right, we show layers and maps and so forth. It can be free, and some of it's subscription based. Kepler, if you haven't heard of it, it's a pretty new product. It's pretty polished, pretty neat. It's developed by Uber, actually, the company that's taken over kind of where taxis left off. But it excels at large data, and it's really good at exploratory data and analysis. You want to see it, you want to look at it, kind of a thing. A couple other ones, Power BI and Tableau. Again, these are things that I've used. We've stood up Tableau instance and actually I used it as a way to work with sponsors. To me, these are really helpful as exploratory data and analysis tools, or what I call capture and discovery, when you don't necessarily know a lot about the data, but you want to interrogate it and see what it has. Next slide, Chris. So we really have a myriad of different platforms and tools to choose from, but it's the question of what approach best fits the need and when we need to go custom. So as Chris mentioned, spreadsheet tools can be pretty powerful. VBA is a very powerful language. It assumes that most users have the software installed locally. They're helpful when you need some quick, rapid type development, when it has a familiar user interface. But the access to external data and geospatial are somewhat minimal. And I'd also say the data size is somewhat of a constraint too, depending on what your local system has. So the other types of tools I talked about, Power BI and ArcGIS. Again, sometimes I put some of those power user tools under the exploratory data analysis category, and this works quite well when little is known about the data, or sometimes the objectives are vague, but you mainly want to do some capture and discovery and see, well, what's the data telling me? They're also useful. I find them to work in organizations where analytics are largely independent from one another. Maybe data sources are more fragmented. They do assume, however, I'd say for both Power BI and Tableau, that you have some time to learn how to really use those tools, and they require some expertise. So next slide. This kind of gets us to where we land with some of our sponsors and some of their requirements. And this is to build custom web applications. What comes with that is both the domain expertise and the computational and development expertise that PNNL brings to the table. So we'll work with groundwater scientists, atmospheric chemists, do some work for DITRA, which involves weapons of mass destruction. So we have both the subject matter expertise and the computational expertise. We used what I call managed cloud services, and that is Azure, AWS, and Google Cloud. These are administered and somewhat monitored within the PNNL framework. So we are fortunate to be able to kind of leverage some of PNNL's expertise in how to set these up, how to administer them. And we use something that is called VPCs, Virtual Private Cloud Network, with our PNNL. So we really have the benefit of what external users using commercial platform might not have, and that we work with our group. So I see these as being modular and extensible. That is, when we build a certain capability in one cloud system, we can translate a lot of that knowledge to another project. Some examples of the domain space we work in is environmental management, which we're talking about here today, electrical grid emergency response. We have a project working with chemicals of mass destruction throughout all of Asia, and we kind of borrow from one another as we build different applications. Next slide. So I consider these, when to build a custom application, I consider these to be very targeted vertical applications, in that they are intended to meet a very narrow needs for a vertical group of users that have very specific and targeted analytical needs as an entity or as an objective or as a group of collaborative partners. We go into these projects with extensive user experience, UX, UI, elicitation, and outreach. So the requirements gathering period up front is pretty extensive, because we don't want to start developing against something that we don't really know the requirements for. Many of these are very tightly coupled with regulatory requirements. So in the case of the application that Chris was talking about, it's something that we call Plato, which is in Socrates. It is directly tied to some of the EPA requirements for remediation standards. So that's built into the application. When we build them, we can transfer to different cloud accounts. So for example, the project I was mentioning in Asia, when that is finished, when we deploy it, we will create a deployment package and we will send that to them, and it's theirs, and they boot it up on their own system. So that's really some of the ease and flexibility of using cloud that I think is really helpful. We build and deploy modern focused analytic services. So these are, you'll hear, or if you haven't, it's as a service, platform as a service, analysis as a service, data as a service. And this is more what we are kind of trying to do. And I think this carves out a kind of unique space for us in that we bring, again, both some of this domain expertise and the computational team to pull it off. So we have very specific targeted services to meet really defined needs. We use role-based access and profile management across our cloud applications. So we can limit access by roles. We can create certain different groups. So we can provide access different features within an application to a broader group. And that has implications for official use only data, sensitive data, and other types of information like that. Next slide, Chris. So the question comes up, sort of migration to the cloud. About 4 years ago, everything that my team was building was on premise. And the question came up, do we move to the cloud? What are the benefits? And in fact, there may be many in the audience here or participants that have something running locally that are wondering if it's right to move to the cloud. So that's a question that really takes kind of a lot of thought and sort of understanding the advantages and disadvantages. With my work and the work that I was doing with my team, it made sense in all of those to move to the cloud. So I mentioned this idea of serverless, and that is just one concept in the cloud, but lift and shift, moving to the cloud doesn't necessarily mean you're going to take exactly what you have locally and just host it on the cloud. Sometimes it means actually sort of reinventing your entire concept of how the application is built. So we, to the extent that we can, we started using something called serverless. And serverless, it's maybe relatively new, I guess the last 4 or 5 years or so, but it seems to be growing. When cloud computing started out, it was really based on VMs, virtual machines. That is, the e-commerce AWS was doing so much business, they had to build machines quick, so they used the cloud to start building virtual machines. And everything was done on a machine, for example, Windows or a Linux machine. Serverless is the idea, however, that you don't really have a machine at all, but you're rather borrowing resources from many, many different chains just to use something as you need it. Advantages are that the resources can be allocated on demand as opposed to running a virtual machine all the time. They are pretty cost effective in that they scale to the user base. So if you're not using it, you don't pay for it. This maintenance assumed by cloud provider and customer, this is really important when we start talking about security, in that we use what's called a shared security model. PNNL does. That is, the development team bears the responsibility for how they've configured their application and what they're using. AWS and their platform as a service, they're holding themselves much more accountable for the security aspect, because you're essentially not spinning up your own computers and VMs, but you're using their platform as a service. So we use that as much as we can. Serverless is very elastic and very scalable. Improved productivity in that you have an endless number of machines that are always turning on. So if those in the group know what Kubernetes is, or Docker orchestrators, that type of thing, those really have value in the right time, place, and setting. But using serverless gives you something like that, in that it's always working. So there are times, however, to use virtual machines, and there's a good time to use them. We have a example today, which we are using virtual machines to do the work. Next slide. So I just wanted to just talk through a couple kind of key features, or some of the components of cloud computing. This is specific to AWS, and I give this as an example because we have more projects right now in AWS than we do Azure or other projects. But I'm wanted to try to sort of relate each one of these to what you might use in a more native environment. So S3 is AWS's storage environment. I treat this really like a glorified FTP. It's an excellent place to go share data and be able to provide access. It has very, very finely tunable access. So you can control the ability to read, to write certain folders within folders, which you can't necessarily do on the FTPs, but you could. Even more than that, it's a place to keep unstructured data. So a lot of our data, as Chris said, some of it's structured, it falls into relational database. Some is NoSQL, falls into some NoSQL database. But then a lot of times you have spreadsheet, SCVs, pictures, all kinds of stuff. That's where S3 buckets come in. EC2, Elastic Cloud Computing, these are in essence virtual machines. There are a whole bunch of extras that come with using a virtual machine. You can program them to turn on, you can clone them, you can replicate them, you can do all kinds of things with them. You can get them to work in concert with one another. Lambda, the next one, that's really at the heart of serverless. It's in Azure world, this is called function. I don't know what it is called in Google Cloud. I'm just learning that environment myself. Relational database service, this is something that we use quite a bit. This is a platform as a service, and it's mainly for relational database systems. So this would be Microsoft SQL Server, Postgres Server, MySQL Server, anything that really that has inherent referential integrity. works for that. So we use it because some of our sponsors have Microsoft SQL Server, and we need to be able to connect with those databases and talk to them. So it's a nice solution. It is a platform as a service. Very little maintenance involved in our end, but we use it. We also use Dynamo database, which is Amazon's NoSQL. Unstructured is probably a misnomer. It is structured, but it's a NoSQL version based on key value data. CloudWatch is a monitoring service not only for all the applications, but it also can provide some cue to us as when something has happened and something we need to know about. Cognito, another component we use from AWS, which is a way we create access and authentication to different parts of the suite from our tools. Next slide, Chris. So here I'm just showing you in the ecosystem how these all might fit together. Talk a little bit about how they're different from a native platform and how we use it. This is actually pulled directly from an application that we're working on. The application, Chris is going to talk about it, deals with remote sensing data, but we use CloudWatch so we know when there is new data available from the owner. In this case, it's satellite data. As soon as that data becomes available, we have a process that imports it to our AWS S3 bucket. And as soon as it's in the S3 bucket, that sets off a trigger for this Lambda function, which is serverless computing, to do some analytics with it. It sends the results of that to two different virtual machines. One is Windows, one is Linux, and it does some processing that needs to be done on those machines. Importantly, before I forget, it turns those machines off as soon as it's done. So if we only get data once a week and it takes a half hour to process, it turns on the virtual machines, processes the data, and then shuts them off. So we're not running them. There's another Lambda function, and then the output of all of that goes to another S3 bucket. And then from the S3 bucket, we serve it out through something called API Gateway and Lambda functions to create web applications. So this really is just talking kind of beginning to end of what are the components of some of the cloud that we're using and how they all fit together to create an application. Next slide. Sometimes rather than creating an interface where the user has to click things and so on, we expose the API directly. And this is in the case of what I think of as power users. They want the analytics and they want to work with it. And so it's a very streamlined page to get to. We have a project running right now that is working with two different national labs in Department of Energy headquarters, Office of Electricity, and Puerto Rican Power Authority. So everyone's got different models they're running, and we want to be able to share all this data. So we use the cloud to do that. We expose the APIs directly. We provide some instruction as to how to use it. And so the power user are able to get right to it, run the analytics in the same environment. Combine this with some of our role-based access so that only certain users can see certain APIs and certain users only have access to certain buckets within the API. It's excellent for data integration and assimilation, and it excels at facilitating collaboration across different organizations and different compute environments. Next slide. Profile management, and I think this is my last slide here before we go back to Chris. In our applications, we use something called profile management. In its simplest terms, it's kind of like Netflix or some kind of program where you have a profile and you log in and you have your preferences, your setting, and you can keep those through all of them. This is, we use this in most all of our applications. It allows for unique data access. We can have specialized functionality, predefined styles. We can save the work, for example, or save the queries here. We can save contaminants, waste sites, as that relates to the Hanford area, colors and styles. You can do work in that session. You can close down, and then when you log back in, you open it up. So profile management is, it gives the appearance that it's much more like a native application, that it's always running, it's saving your data, it's saving your material. In our applications, you can share the output of your work with another user. So you can do some work and then email it to somebody else. They can pull up the application, and you'll be sharing exactly the same process that you've gone through to get there. I think you're up next. I think you're on now, Chris. Is that true?
Yes.
All right.
Patrick. So that gives you some context for a web-based cloud computing infrastructure. Now I'm going to talk a little bit more about analytics for environmental decision making. So the web-based applications, they can provide this availability and convenience and rapid assessments. And another key thing is that there's consistency and reproducibility in analyses. They incorporate, as Patrick mentioned, regulatory guidance, and it's easily available and reproducible. Another key feature about web-based applications is the interoperability of tools and data. Patrick talked about how we can do all kinds of different things with the cloud computing in terms of turning things on and off and sending data here and there. So that's a key feature. These web-based applications provide a good vehicle for communication with other technical staff, with management, or regulatory personnel. And that could be, sharing or putting things into reports, or just, providing the URLs so they can see those applications. And all of this provides a basis for supporting environmental decisions, which feeds into various approaches such as adaptive site management of complex sites. So I have some examples of tools I'm going to go through to support decision making. These analyses are based on published guidance, such as from EPA and standard statistical methods. There's sort of two categories. One would be data access and visualization, and the other is rapid data analytics. So if we think about environmental data again, we're typically looking at things like groundwater, plume, contaminant concentrations, water levels, and so on in the groundwater, looking at wells that give us the view into the subsurface, what's happening at waste sites, what are we doing with remedies, and what kind of remote sensing, what does that tell us? And all this supports different decisions about things like exit strategies and endpoints. When are we done? Do we need to optimize a remedy? So do we need to take our current remedy and switch to a different one, be adaptive over time? And overall, the decisions we're looking at with these analytics are to help protect human health and the environment. So this is an example of access and visualization of groundwater data. In this particular case, we're looking at either time series or depth profile visualizations of groundwater data, where we have the data displayed in a chart. We can look at multiple different parameters here for a specified time frame. And we can even do things like filtering the data based on some attributes such as reject data, or if we went out in the field and we had collected filtered samples versus unfiltered, we can filter that in the application and show that in the time series data. We can include water table or river level information for reference, so we can see if there's any correlation between changes in concentrations with changes in water levels or river. And we can export all this information, either the figures or the data, for reporting purposes. And again, all this is used in context of remedy guidance, such as an EPA document from 2013 that talks about when are you done. So this is that was the time series picture. This is a depth profile image here. And again, this kind of information can be used to make some decisions about your remedies. If you're looking here and you see that there's deeper contamination than what your current remedy is getting, then you may need to reconfigure or optimize your remedy so that you capture that additional contamination. We look at access and visualization of 3D geology. So this would be where you take a site and you pull out a 3D segment to look at the subsurface structure, geology, the hydrogeological units here, where you can go across the site and look at point elevation information. What's the depth to water table? What's the depth to individual geological unit in a particular location? We can look at cross sections. You see for the upper right here, there's a cross section line with the magenta point indicating where it's located, and see what that looks like. And all this informs your conceptual model, what's happening in the subsurface, where's contamination at, how we're going to approach this. And this links to other tools to provide that context for making decisions about remedies. Water level and flow direction analysis is another key aspect that informs your conceptual model and helps you make decisions. You're looking at groundwater elevation data to figure out where's contamination going. You have a particular location. Is it moving? You know, what's down gradient? Where's it going? Are there seasonal effects that come into play? If you're perhaps near a river, for example, you might have water tables going up and down and the flow direction changing over time. So, and you could be looking at things like how fast is this going? How much time before it reaches a receptor or a compliance point? Then we can take that sort of information and help inform our attenuation capacity analysis. So if we have contamination that exists, this little pink blob down here, for example, we might want to look at along a flow path down gradient. Does that contamination get attenuated and at what rate, so that we can determine that attenuation capacity and make decisions about whether or not we can turn off our remedy. So if we can back calculate given a threshold, target concentration at our receptor compliance point, we can back calculate and say, based on the attenuation capacity, we need to reach a concentration of, in this example, I have 35.5 micrograms per liter at the source area before we can be confident that that will meet our objectives, remediation objectives. Or we could look at mass flux would be another item. And again, this is based on guidance from EPA and Truex et al. We could look at a contaminant plume more broadly in terms of plume analysis, say what is the plume behavior over time? And this is a good example of something that you might have done in Excel or on your own with data, but it takes quite a bit of time to parse through that data and get the right kind of information, where we've built into the tool things to look at temporally consistent well sets. For example, down here, based on when wells were installed and what the project scope is and budgets, you might sample wells at different times over the course of years. And you really need to look at a temporally consistent set of wells to understand a trend in that plume. So here we've selected a set of consistent wells and we get a trend over time, and it gives us information about what is that attenuation rate, which tells us things like what's the time to completion, or are we already done, right? Is the remedy working, or do we need to go out and optimize the system to catch elements that are not being captured or improve the performance? And again, based on published guidance here. This is another example application, and in this case, we're looking at aquifer injection evaluations, where a produced water, such as a brine, could be injected for disposal. And this particular tool provides information on the area of impact using a variety of methods that look at displacement, dispersion, groundwater flow effects, density differences, and so on, to give you an estimate of what is that area of impact. So that if a oil and gas producer comes to you with, here comes to EPA in this case, with a request to dispose of brine in an injection well, then there are tools that can provide the analytics to say, well, this is what we estimate the area of impact would be. And therefore, if it's going into a drinking water aquifer, we might have to have an aquifer exemption. And so that this all leads to decisions about that disposal approach and how big does the exemption need to be? Is that appropriate? It's really looking at those kind of questions for aquifer exemptions. And this gets back, this example here is the remote sensing example. It gets back to what Patrick was talking about in terms of how the web-based functionality is tied together. In this case, we're looking at satellite data, which is consumed, processed, and provided to the web application through automated processing that when data shows up, it gets processed and is made available. So in this case, there's a couple of kinds of data that can be visualized here. One would be temperature data to look at temperature and assess. In this case, they're looking at along the river here. What can the temperature tell us about migration of groundwater into the river and in terms of flux of groundwater and potentially contaminant? So we have a visualization of the plan view of the data, as well as cross-sectional information over distance down here. You can also look at things like surface elevation and how does that change over time. So in this case, you'd be looking for subsidence, whether you might be looking at a particular waste site to see what's happening over time with that waste site. And you can set up the web-based tool to provide an automated alert as well as the automated processing, so that if you're looking at a particular area of interest, it will send you an email that says, hey, in the last time period, things changed more than your tolerance. You should go take a look at this and make sure that you know what's going on. So I'll talk a little bit about the conclusions and benefits then. You know, again, environmental professionals and managers, we need tools to not only access this environmental data from groundwater and remedies and so forth, but we need consistent quality approved approaches. All right, again, I get back to the quality where the data and the software have to be vetted and trustworthy and credible for making decisions. And so we can, you know, we're supporting those decisions and we're communicating again with other technical staff, management, and regulatory personnel to say, these are the analyses we've done based on this data, and this is what it tells us in terms of how we're going to manage environmental decisions. Web-based applications for subsurface remediation provide, they minimize complexity associated with large data sets and analytics. They maximize the consistency and productivity, again, promoting the technical communication either through sharing or reproducibility, availability that folks can go out and see this for themselves. And they provide robust and reliable performance with the web-based cloud computing. And then finally, provide a technical basis for that decision-making of where to go from here. In terms of impact and broader application, we can think about the data management, resilience, and adaptability. So we're talking about potentially large volumes of data. You know, as time goes on, we're getting more and more data, whether it's satellite sensor data, or climate data, so on. It's a lot of data to deal with. And so web-based tools provide ways to deal with those large volumes of data. And they provide a variety of analytics to answer the questions that help you make your decisions. And we've talked about the user experience too. That'd be another thing that these web-based tools can adapt to changing human interaction patterns. Cloud computing and serverless architecture really provide those robust and rapid analytics. Everything from simple analytical methods to more complicated machine learning. And they do the big data processing, integrating those disparate data types, pulling those different kinds of data together to do the analysis, make some decision, whether it's relational or unstructured data. And these kind of tools, you know, we've talked about environmental management and environmental decisions, but they can really just be used in a range of contexts. We could be talking about water resources or other natural resources, how to manage those, make decisions about those. looking at climate resilience or disaster response. So these are useful tools with robust features applicable to a number of different domains. So here's a list of references. We'll throw that up here for a few seconds so you can take a look at that or come back to the video later. And that'll be the conclusion of our presentation. So thank you.
Great. Well, thanks, Chris and Patrick. I appreciate that. I'm going to start off with a couple of questions, and if anyone has any questions, feel free to paste them into the chat. So the first question I have is, how does a cloud-based implementation compare to an on-premise server in terms of security for applications and data?
Patrick, I'll let you take that one.
Sure. Thanks, Alicia. I'll try to give you a very succinct answer so we can get some more questions in. I am neither myself or Chris are the experts in security or cyber security. So we rely inherently on our cloud team to sort of administer that and provide some guide rails for us. One way that they differ, as I said, is it depends on what type of service you use. So we have a shared security model. The more you use a platform as a service, you're sharing that responsibility with the cloud provider and yourself. The more that you're spinning up your own virtual machines, you are inherently responsible for all the security related to it. So I guess in summary, we work really tightly with the cloud security group to set those up and administer them.
Great, thank you. One question that just came into the chat from Karen Studaris was, first, she says, thanks for showcasing these great tools. How much turnover do you see in your user community? For instance, have the folks that gave specifications in the development of these tools continued to be the individuals who use them?
So I'd say the specifications don't typically come from the users. I mean, some of them will, but a lot of the analytics are driven by guidance documents, such as from EPA. PNNL has produced some guidance documents on things like soil vapor extraction and pump and treat. So a lot of the underlying things will remain the same regardless of the user base. There are and can be a lot of turnover in users. Just depends on the waste site, the contractors that are involved, and so on. And that's where these tools are great at providing accessibility and consistency as you get different users.
Great, thank you. I have another question in the chat from Ingrid Burgesson. So is this like a database setup where you need to know what's going into the project in terms of what you have and what you want, or is it more facile and you can kind of build as you go without the need to redesign?
Patrick, I'll let you take that one.
Me?
Yes.
Yeah, sure, got it. Just for clarification, what was the question about redesigning the database?
Yeah, I guess it's more along the lines of, do you need to have everything do you need to know everything up front, or can you kind of build as you go?
Oh, right. Okay. That's a very good question. Okay. What it helps to know is what type of data you're working with, if it's structured, unstructured, if it's relational database system or not. So there are a lot of times you intentionally build an application with fake data because you know it's going to take so long to get that data. So the answer to your question is no, you do not have to have everything up front. It is very helpful to know at least what kind of data you're working with. So there's been some examples when it's taken us so long because of the security involved in getting a direct connection to someone else's database that we never actually get that connection set up until we're almost done with the project. And in that case, we have set up the schema for what the data looks like, the fields that we have, the parts that are structured, the parts that are unstructured. And so that way we can start moving along. If in fact we had to wait until we had everything until we started developing, we would probably never get anything done on time. So, anyhow, very good question.
Great, thank you. Another question that came through the chat is what platform is used to build AIM? AIM?
So that was built on AWS as well. It is not quite as complex as some of the other tools in terms of, I showed the remote sensing workflow. The AIM tool is based on some analytical models, but it used the AWS platform.
Great, thank you. I have two other questions here. One question, how do you protect OUO or official use only data?
Yeah, sure. I'll answer that. Another excellent question. So this gets just a little bit tricky in that the access to OUO or how it should be accessed, some of that is identified by the derivative classifier for that project. So multi-factor authentication to begin with. That's probably one of the more robust ways to protect it. And sometimes we do 3-level authentication. I do have a database where I do have a project where we're using 3-level authentication. So one is IP filtering. That's based on where you are. Are you a part of this? With other labs, we get their IP. And we only allow access to that IP. Then they need to sign in with authentication. After they sign in, they get that third piece, which is a text message on their phone. So that's a multi-layer protection in terms of just accessing it. Protection of the data in general and where it all stands, that's protected by building our own VPC. That's a virtual private network within PNNL. So we eliminate any kind of peer-to-peer sharing to the extent that we can. So with the data is naturally never out in the world, where other peers can get to it. So again, so that's protection of peer-to-peer sharing by virtual private cloud, implementation of multi-factor authentication, even up to 3 factors of authentication. So we do have projects, OUO and sensitive data. The extent that it needs to be protected is sometimes directed by the DC of that particular project. But it's an excellent question. It needs some more time because as these tools are evolving rapidly, we need to kind of regroup very quickly and get back together with the DCs and understand the lab what's the best approach.
Great, thank you. And just for folks that are outside of PNNL, Patrick, can you explain just very briefly what a derivative classifier is?
I'm sorry, a DC. This is the person in a project that helps us basically understand what our OUO data is. Sometimes will tell us if the data is official use only, and generally works with us to make sure we're applying best practices to use official use only data.
Perfect, thank you. This is a really good question, actually. I've wondered this myself, but if I want to include a figure from a web tool in a report, how can I link that figure back to the details of the data source and analysis?
Yeah, so that gets into the data provenance that I was talking about in the quality aspects. So a good approach for that would be, I talked about we can export figures for inclusion in reports. So including as part of that figure, some footnotes to say this is the application this came from, the dates, the database, just including that information in that figure as essentially footnotes would be a good approach. And yeah, so that's probably the best approach. There's some things we can do in terms of maintaining copies of data and referencing dates for when data is updated and when it's changed. So that'll provide some additional information about that traceability. So.
Yeah, I would just add to that. That is a very good question. So the idea of creating that stamp when you do it, the metadata, and we're actually doing that this year right now because that question arose, Alicia. And so we're creating some kind of metadata traceback. What's a little more complicated, and I guess what people don't have time to answer, is this idea of database snapshots. So in an environmental monitoring database, the data may have been collected 10 years ago and you have all those records, but it can just be this year that somebody else went back and changed some information or record that was entered 10 years ago. So that idea of snapshotting becomes a lot more important. That's very costly to do, and that is an aspect of it that probably deserves some more discussion in terms of connecting to that database at the same time that that data was created in the event that it had changed after the fact. So kind of a question with another question, but it's an area that needs some consideration.
Excellent. All right, great. We've had 2 additional questions come into the chat. So we're going to end with those 2. The first one, how detailed does the geologic information need to be to get accurate results from AIM? How much detail can AIM handle? 1D, 2D, 3D?
AIM is a relatively simplistic. In that project, we looked at some 3D numerical modeling with STOMP. It's a code developed at PNNL for multi-phase flow and transport. And we compared analytical solutions to the STOMP model. And there's clearly some things that, AIM will just look at some basic information. It makes a number of assumptions that we lay out in the user guide in terms of an aquifer of a certain, you define the thickness of the aquifer and the type of material, the hydraulic conductivity, and so on. But it does not go into additional depth for heterogeneity in the aquifer. You can probably deal with some amount of stratification in terms of simplifying assumptions that you can live with. But there are some limitations to what it does. But that was mainly based on what the project scope was and the intent to have this relatively simple tool for that analysis. That's not to say you couldn't, with additional funding, you could expand that, because there's a lot of capabilities with the cloud platform to bring in more complex numerical analysis.
Great, thank you. One final question. What future work or plans are there to expand Socrates to work with other remediation sites other than Hanford?
So we're definitely looking at that. As I talked about the impact there, I was talking about other domains, but certainly Socrates and these kind of tools for environmental decision making fit well with other sites, both within DOE and DoD and private sites. So we're definitely looking at that, and would welcome some other opportunities. The nature of the cloud application is such that we can connect the right data and provide these analyses for different sites.
Yeah, it's worth mentioning Vicki Friedman is heading up a project track, which is for Department of Energy headquarters, and it is an overview of all of the sites. So that there is some, it's not as analytical, it's a viewer, but that's in motion right now.
Great. Well, thank you, Chris and Patrick, and thanks for all the excellent questions. We want to thank everyone for joining our seminar today. And just a reminder that the seminar will be archived on the RemPlex website. We encourage you to sign up for the RemPlex newsletter by sending an email to remplex@pnnl.gov, and to join the LinkedIn group using the link that I put in the chat. And also, please join us for our next seminar on April 28th on informed optimization concepts for enhancing groundwater extraction and recirculation remedy performance. That's presented by Arcadis. So thank you again and have a great day.
Thank you, Alicia.
Bye. Thanks, Patrick. Thanks, Chris.
Thank you.
Bye.